Hi, my name is Lori, and I'm a support engineer with GeoSlope. I've created a series of getting started tutorials for new users to GeoStudio. So if you're brand new to using the GeoStudio software and you're not quite sure where to start, then you've come to the right place. These tutorial videos have been designed to help walk you through the basic steps of creating a simple model using GeoStudio. The main topics that will be covered in this series will be how to use define to set up a numerical model, using the solve module to compute the numerical solution, and how to use contour to view the results and to gain a deeper understanding of the problem you're modeling. You can pause, stop, fast forward, or rewind these videos at any time by using the controller bar positioned at the bottom of the window. If English is not your first language, you might find it helpful to print out a copy of my script, which is available as a PDF from our website. So let's get started. Potential evaporation is defined as the amount of water that could be evaporated if there was an unlimited source of water available. However, water does not always evaporate from the ground surface at the potential rate. When a soil becomes unsaturated, the water is not readily available. The actual evaporation is considerably less than the potential value. VADOSE is a rigorous finite element program that links the stress state of the moisture in the ground to the demands of the climate and computes how water moves through the soil and across the soil-atmosphere interface. Early in the development of potential versus actual evaporation theory, a laboratory experiment was conducted in a climate-controlled chamber. The temperature and relative humidity were carefully regulated, and the evaporation from both an open pan of water and a sandy column of soil was monitored. The VADOSE Getting Started lesson is a simulation of this laboratory experiment. The numerical model is quite simple and consists of a one-dimensional column with a total height of 30 centimeters. The top of the column uses a special type of region called a surface region. Climate boundary conditions can only be applied to surface regions, so all VADOSE models must use this type of region across the ground surface. The initial temperature of the soil profile will be specified as a material activation property of 38 degrees, and a water table will be used to specify initial pressures in the column. The model will be run for 40 days of climate data, where the climate data represents the potential evaporation, temperature, and relative humidity that was measured and monitored within the controlled climate chamber. It's interesting to note from this simple example how much information and understanding you can get by setting up a simple analysis to test theories and conduct preliminary modeling before moving into the full two-dimensional simulation. We are going to start by selecting a VADOSE analysis from the Start page of GeoStudio. The Key and Analyses dialog box will automatically appear. Close it so that we can start creating the model by defining the page, scale, and units information. To set the working area, select Page from the Set menu. The working area defines the size of the space available. The working area may be smaller, equal to, or greater than the printer page. The next step is to set the scale in units. We are going to use metric units with kilojoules, days, meters, degrees Celsius, and kilonewtons. The scale should be set such that the minimum and maximum extents in VADOSE match those required for the analysis. In this case, the column was only 30 centimeters high, so a very small scale is required. Regardless of the magnitude, the best approach to use is to define the X and Y minimum and maximum extents to find an approximate scale, and then fine-tune it to use a 1-to-1 aspect ratio. Now that we've set the units and scale, go back into Key and Analyses. We're going to conduct a fully coupled analysis, which means that the equations that the software will solve will include both water flow and heat flow coupled with the vapor pressure in the soil. The initial pore water pressure conditions in the column will be taken from an initial water table that we will draw. Time steps are very important in a VADOSE analysis. The time-stepping sequence is important because there can be very steep drying fronts with high gradients. We will set up the model to use 40 one-day steps. However, we will also use adaptive time stepping, which will insert additional steps as necessary, so that the model can converge to a reasonable solution. In this case, the adaptive steps are allowed to vary between 1e to the minus 4 and 0.04166667 days, which just happens to be 1 hour. Control of the adaptive time stepping is set to allow a maximum change of head of 5% between any two time steps. The first time you start working with VADOSE W, it's helpful to learn what different toolbars exist. In VADOSE W, many of the drop-down commands are also available as individual icons on the many different toolbars. You can familiarize yourself with the toolbars by toggling them on and off. Before defining the geometry, it's usually helpful to sketch an axis. Use the cursor and the coordinates shown in the bottom right corner of your screen to locate the origin on the page. To sketch the problem, select Polylines from the Sketch menu or use the Sketch Polyline icon. Use the cursor like a pencil, clicking the left mouse button to create a series of lines to outline the problem features. The lines are objects which can be adjusted or deleted using the Modify Objects command. And it's a good idea to save your file frequently. The approach to use when developing a numerical model is to draw the geometry, create and assign materials, create and assign boundary conditions, and then finally to review and fine-tune the finite element mesh. Let's start by drawing the geometry. Individual soil regions are created using the Draw Regions command. Click the left mouse button to create region points. We are going to add a special layer called a surface layer, which will allow us to use a climatic data boundary condition. Choose Surface Layer from the Draw menu. For this simulation, we are only going to use one layer, but you could apply several and use different materials assigned to each one. Drag a box around the surface points or hold the Shift key down and select the starting and ending points. Choose a thickness. Materials are first created and then assigned to geometry objects. Choose Materials from the Draw drop-down menu. Click on Key In to create a material. For this analysis, we are going to use a simplified thermal material model, which means that we can define simplified thermal constant values instead of functions. But we'll still need to define both a hydraulic conductivity and volumetric water content function for the hydraulic properties. The ... button is used extensively in GeoStudio to indicate that additional features can be accessed through this button. Click on it to define the hydraulic functions. For this analysis, since we're simulating a laboratory experiment with published data, we need to copy measured data points for the volumetric water content function from a spreadsheet. The spreadsheet is available in the Examples folder of GeoStudio. Highlight the volumetric water content data points, Right-click to select Copy and then paste the points directly into the function list box in GeoStudio. The m sub v for the function was 1e to the minus 5. The connectivity function will also be taken from published data for the experiment. Incidentally, it is possible to predict the conductivity function from an existing volumetric water content function directly within the software. If you want to know how to do this, watch the function estimation movie available on our website. The functions have now been assigned to the soil, and the material can now be assigned to geometry regions. Boundary conditions are created and assigned in the same way materials are. Select Boundary Conditions from the Draw menu. The boundary condition we are going to create is a climate boundary condition. In VADOSE W, climate data is defined as a data set. Once again, we want to use information from a lab experiment, so we'll return to the same spreadsheet and retrieve the climate data that was measured in the lab over the 40-day period of the experiment. The climate boundary dataset has now been created and can be applied by clicking on the geometry object, in this case, the top of the surface layer. Now the geometry has been drawn, the material properties have been created and assigned, and the boundary conditions applied. It's time to review the finite element mesh and make any necessary adjustments. You can view the finite element mesh using Draw Mesh Properties. The meshing algorithm in VADOSE W is defaulted to use a global element size. Since this is a one-dimensional analysis, we want to control the mesh, to use a rectangular grid of elements, and to have 10 centimeter increments along the y-axis of region 1. We also need to break up the surface layer to use 2 vertical elements, and to have the column be 1 element wide. Once you have applied a meshing constraint, you will see a visual indicator showing which geometry object has been constrained. In a two-dimensional situation, it's often best to start with a default mesh and then constrain the mesh only if it's necessary. The finite element mesh will disappear after you leave the Draw Mesh Properties view. If you wish to leave it on, you can click the View Mesh icon on the View Preferences toolbar. Now we need to define the initial water table. Choose Water Table from the Draw menu and use the mouse to place the water table just below the soil surface. Now it's time to solve the analysis. Click on the Solve icon found in the Current Analysis toolbar. You can view the results directly by clicking on the contour icon in the Analysis toolbar. By default, the contour results will include velocity vectors and pressure head contours. The ability to graph information is very important in a 1D model. It can help verify the climate input and to help you understand what is happening in the system so that you can have increased confidence in your engineering interpretation. The main purpose of this experiment was to highlight the difference between actual and potential evaporation. First, let's draw a graph of actual evaporation versus time. To create a graph, choose Graph from the Draw menu. Choose what type of graph you are going to create and then select the location where you want the data drawn from. In this case, we're pulling the information from surface region nodes. Now create a graph of the potential evaporation data for the surface region nodes. This data will correspond to the input potential evaporation values that were measured in the lab from the pan of open water. By holding down the Control key, you can view both the potential and actual evaporation at the same time. Notice how initially, when the column was saturated, the evaporation from the soil surface was near potential. But then after about day 10, the availability of water was restricted and the actual evaporation from the soil became much less than the potential evaporation. Now let's draw a graph of matrix suction versus time. When the suctions at the ground surface start to increase rapidly, it corresponds to the time when evaporation also shut down. In VADOSE W, it's very important to know if you're looking at a good numerical solution. You can review the solution by looking at the water balance error. If the water balance error is minimal, it's a strong indication that the model has solved well. Let's create two convergence graphs, one showing the water balance change in storage within the column, and the other showing the water balance evaporation. In this case, the amount of water considered lost from storage is equal to the amount of water that left the profile due to evaporation. You can see this when you plot the two graphs together. They lie on top of each other, which is a good correlation. New to GeoStudio 2007 is a reporting feature. If you need to generate a report of your input for a particular analysis, select Report from the View menu. Once you save the report file, your default word processing program will open with a generated report. You can now insert pictures, apply style templates, or add and delete data. If at any time you need help with understanding a dialog box, you can click on the question mark in the top right corner to access the online help, or use F1 on your keyboard. You can also switch to the Analysis Start page, which has PDF copies of all the engineering books for GeoStudio under the Documentation section. These books are very helpful in describing the features of the software and the theory behind them. You can also search through the examples database using specific keywords. And when you're done, you can return to your analysis by clicking on the analysis list. We have reached the end of this introductory lesson. Not all of the powerful features of VADOSE W have been used or discussed during the lesson. Specific details about each command are given in the online help and in the supporting documentation for VADOSE W. Thanks for watching.